Okay, we are now recording. Let's go to current slide. But before we do that, Corey, you haven't heard this one probably, but the others have ad nauseum, but I'll still announce it again. This came from Dr. Wilson here, who got it from a postdoc at UAB in microbiology, I think, yeah. Dr. Christina N. Mora sent this and said she's one of the newest cohorts of the merit scholars at UAB. And here's what she said. I came across this one-week summer opportunity for college students interested in biopharma manufacturing careers. I assume that's pharmacology, the making of drugs, I assume. And thought one of your students might be interested in applying. The students are paid $1,000 for 1 week, and the travel expenses are covered. The application deadline is January. They don't say when, but I have a website you can go to and find all the information you might need.
What if you're not in that field?
Yeah, I'd say if you're interested, apply. This sounds like too good. 1 week, 1 week in the summer, they pay you $1,000 and travel. So it sounds mighty good. So I would say, come get the website and you can look it up. Okay. Now we've got projection. Okay, where we are now, we're in Chapter 4, Higher Order Differential Equations, and 4.3, Homogeneous Linear Equations with Constant Coefficients, and we're getting ready to start example 1. That's where I had it anyway. Any questions on anything before we get going? Okay. Okay, example 1. Solve the following differential equations. See, up until now they've been saying, here's an equation, here's a solution, blah, 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 blah. Now we're finally getting to solve them ourselves. Let me get my pen set up. Okay. 2y double prime minus 5y prime minus 3y is equal to 0. Okay? How would you begin? Say that one more time.
You put it in like the auxiliary.
Yes. Okay. And what would that be? Now, yeah. Now, here's the thing. I know the book doesn't really suggest that you do this, but I like to say, where does that come from? Your assumption here, because this is a linear, higher order differential equation with constant coefficients, you're assuming that y is equal to the form of e to the mx. Okay? With that done, what's your auxiliary equation? You were starting it. 2m squared minus, unless I'm copying, yeah, minus 5m minus 3 equals 0. Now, what do you do with that? Say again? Quadratic formula? I would kind of like to see if I can factor it first. Can you factor it? How does that go? Yeah, 2m plus 1 times m minus 3 equals 0. Now let's just check that quickly and make sure we did it right. 2m times m is 2m squared. Minus 6m plus m is minus 5m minus 3, yes. So what does that tell you? M is equal to negative 1/2, or m is equal to 3. Now what does that tell you? Okay, so your y, your general solution, will be C1 e to the negative 1/2 x plus C2 e to the 3x. Done. Perfect. Okay? y1 is equal to C1 e to the minus x over 2, or minus 1/2 x, it doesn't matter how you write it, plus C2 e to the 3x. Good deal. All right. This time, just so we'll have plenty of room to write. All right, to erase? Yay or nay? Okay, okay. All right, the B part here, y double prime minus 10y prime plus 25y is equal to 0. Okay? Again, I like to start with, let's assume y is equal to e to the mx. Because you have a linear, higher order differential equation with constant coefficients. Next. Second? Yeah, but what is this one?
It's e to the m squared minus.
Okay, m squared minus 10m plus 25 is equal to 0. M minus 5 times m minus 5 is equal to 0. So m is equal to 5. Okay, so what's your solution? Y is equal to C1 e to the 5x plus C2. Oh, really? Wouldn't that be just C3 e to the 5x then? Or C anything e to the 5x. Same solution. But it's a second order. You got to have two. What do you use for the second one? Okay, go back. Okay, go back to the case 2 on the opposite page. Repeated real roots. Oh yes, you put an x in the next one. Plus C2x e to the 5x. There, your two independent solutions. Two independent solutions. One e to the 5x, one x e to the 5x. You do that with repeated roots. Now you can't go in throwing in minus signs over. Well, let's just make one a minus out. That won't work. All right, good deal. Got case 1 and case 2 done. Let's see what C will bring for us. You got that, or you need it a little longer? Okay. All right. All right. We just did examples 1A and B on page 137, getting ready to do 1C. You can pick it up on the YouTube video afterwards. All right, the C one, y double prime plus 4y prime plus 7y is equal to 0. Where would you begin? Second? E to the mx. I just like to do that to remind myself what to put it back into. Okay, and what you're going to say, your auxiliary equation is? M squared plus 4m plus 7 equals 0. Anyone want to try to factor that one? I think not.
M plus 4 plus minus minus 4 minus 3 and plus 4.
And they multiply to be?
M plus 4
times m minus 3?
M minus 3.
What's the last term multiply to be? What does the last two terms multiply to be?
M squared plus 4m plus 7.
Yeah, you added rather than multiplied. Yeah, won't work. This one will not factor. 7 only has two possible factorizations, 7 and 1, and there's no way you're going to get a 4 out of a 7 and 1.
We just give up on this.
No! What was your first suggestion on the first one? Bill came up with it. No, what was your first suggestion? Quadratic formula, exactly. How does that go? M is equal to minus 4 plus or minus the square root of 16, right, I got it, minus 4 times 4 times 7, isn't it? No, 4 times 1 times 7, I'm sorry. Huh? 7, yeah. Okay. And all over. Whoa! Wait, my pen's messing up. Okay, let me try this again. Okay, over 2. Right. Okay. And what does that give us? Minus 4 plus or minus the square root of 16 minus 28. Oh boy, over 2. This is equal to minus 4 plus or minus square root of what'd you say?
12i.
Well, okay, square root of 12i, yeah. I times root 12, right? Okay. Now, I'm going to go over 2. I'm going to continue over here. That'd be minus 4 plus or minus. Do you see any hidden perfect squares in 12? Yeah, 4 times 3. 4 is square root of 4. 2i root 3, right, over 2. Now what can you do? Okay, so that will give you minus 2 plus or minus I root 3. Now the books sometimes like to do root 3i. I don't like to write it that way because then sometimes I'll confuse myself and think the i's under the square root. So I put the I in front. It's just my little weird thing because I know I tend to make errors. Okay, now what do you do with that? Yeah, yep, you do that. Okay. The only way I remember it well is just doing it over and over and over. So what does that come out to be? Here's, if you look at case 3 of the, well actually just above this example 1, there is the ultimately what it turns out to be. Now, just to get you a background here, this solution to your auxiliary equation is of the form alpha plus I beta, or beta I. I don't care which way you do it. I put I beta because I had the root 3 afterwards. Okay? So the line right above here says your solution is y is equal to, okay, actually go to the second part of it. Factor out the e to the alpha x. You see that? Okay. So e to the, and what's your alpha? negative 2x. So that's on the outside. And then on the inside is C1 cosine square root of 3x plus C2 sine square root of 3x. And again, be careful. My square root of 3s are looking worse all the time. That's awful. I don't know how it came out that way. Okay, let's get that straightened up a little bit. Okay, be careful that you end the house before you get the x in there. Okay, and that's your solution on that.
Okay. I'm just looking at this. What I said, you just assume that that's a 1 always. Now,
Oh, this or where?
right here, right here.
Right.
Okay. Now look what we have in the other part, the
Yeah.
I beta.
Yeah, I probably should have read beta I, but whatever.
Okay, well, I like that.
Yeah.
Well, true, because I know what I do. Okay, when we get up here,
Yeah.
this thing,
This is the alpha,
okay, that's,
e to the minus 2 alpha,
okay,
and then this is the beta,
that's the beta.
the root 3. So,
Now, whatever is before that I, okay, that's going to go up in the solution up there. But we have C1,
Yeah.
C1 cosine square root of
Yeah.
x.
yeah, the plus or minus here results in 2 up here.
So,
C1 and C2.
so if I had 5I, I would have 5 times the square root of 3x or whatever.
Okay, if this had been minus 2 plus or minus 5i,
Yeah.
that would have been e to the minus 2x. That stays the same. The alpha stays the same, whatever that is. This is your alpha. And
Okay.
then your beta would have been a C1 cosine 5x plus C2 sine 5x. Yeah. The only reason that was a root 3 was because of this one. Yes, didn't go out. Yeah. And pretty nice we don't have to go through Euler's every time. You know, once you got it, then it's sort of like those completing the squares. If you have to, go on and complete the squares, but if you can get, well, the quadratic formula came from completing the squares. Well, I don't want to complete the square every time. I'm going to use quadratic formula because that's so much easier to remember. Yeah. So, same thing there. All right, let's make sure the book got it right. Y is equal to e to the minus 2x times C1 cosine root 3x plus C2 sine root 3x. All right. Any questions on that before I go to example 2? All right. Example 2 is a little different in that it's an initial value problem. So we'll solve 4y double prime plus 4y prime plus 17y equals 0, given that y of 0 is equal to negative 1 and y prime of 0 is equal to 2. Now a little bit of review real quickly here on what is required for initial value problems. Okay? If you had a first order differential equation, you only need one initial value. If you have the second order, you need two initial values. Now, what has to be true about initial values? They must be of the same value. That's the initial value. Okay, the 0 for the x. And what is also true is you have y and y prime. You never get up as high as y double prime, just y and y prime, but 2 because it's the second order. So yeah, that's legitimate. All right. What would be your solution? Assume let y equal e to the mx. Okay. Now proceed from there. 4m squared 4m plus 17 equals 0. Any hope of factoring that one? I would say not. The only possible factorization for 17 is 1 in 17. No way you're going to get a 4 out of that, I don't think. Okay? So you do have a leading coefficient, but it's not going to be enough. So what would we do then? M is equal to help me. Minus 4 plus or minus the square root of, which is 16, minus 4 times, 4 times 17. I think you can probably already see this is going to be another, over 8. All right. So let's proceed with that. That will be a minus 4 plus or minus the square root of, say that one more time.
16 minus 272, that's negative 256.
Is that the whole numerator? I mean, the whole radical up there?
Yeah, 256.
Negative 256. Okay, over 8. Now, 256 sounds pretty much like a perfect square, only it's got an I with it. Say again? 16 minus 4 plus or minus 16i. I'm going to write it that way this time because I don't have a radical to confuse me. Okay, over 8, which, clean that up just a little bit. What do you get? Right, it sort of, yeah, but you do the other one too. Let's write it in what they always said with complex numbers in standard form, A plus BI. What would be your A? Minus 1/2. And then your B would be 2I. Got it. Okay. I was just about to put a hat on my I because I'm so used to doing that from count 3. So, but this is not that I. Okay. As if we don't have enough letters in the alphabet. Okay. So what does that lead you to conclude? Y is equal to E. No, let's start with the E. Okay, negative x over 2. I'm going to write that way just because it's a little easier. There's your e to the alpha x. Got it? C1 cosine 2x plus C2 sine 2x. That's it. See how they did? Y is equal to e to the minus x over 2. I figured they were going to do that. Whoa! Oh, wait. We didn't finish the problem. We did the general solution. But,
We didn't do the...
yeah, we haven't done our initial condition yet. So, this is yet another bag of worms, almost. Okay? Now, I'm going to erase that line called, oh, goodness gracious, everything went away. Let me erase that line here because I think I'm going to need the space there. What are we going to have to do here? Let x be 0. So you have y of 0 is going to be 1. Okay, I'll buy that. Then you got a C1.
That's 1.
1.
So C1.
That's all, right? And that's equal to minus 1. Right? Oh, did you finish? I thought you were through.
Yeah.
Yeah. Because this is cosine of 0 is 1. So that's C1 plus sine of 0 is 0. So you got y of 0 is C1. And y of 0 is minus 1. So C1 is minus 1. Now, the next part, though, not quite that straightforward. What are we going to have to do first? Yes. Okay, but what do we have to do first? What was the standard answer in Cal 1 class? Take a derivative. Is that what? Is it right? You got to get what y prime is.
Oh, okay.
Oh, so what is your y prime? That's what I had left room for here, but maybe it'd be better down here. Y prime of x, I'll put, is equal to, okay, oh boy, what are we going to have to do? Okay, you're going to do what? Product rule? Okay, you want to start with the first. That's e to the minus x over 2 times the derivative of the second part. What would that be? Okay. I hope you didn't mind I went on and put the... Okay, good. Okay. Plus 2c2 cosine 2x. See, that wasn't that bad, but that's just the first part. Plus... Okay, you got okay. C1 cosine 2x, C2 sine 2x, second, okay, there's a minus, isn't there? Minus, I'm going to put the minus there and put e to the minus x over 2 over 2. Is that okay? All right. Now with that, we plug in 0 again. Y prime of 0 is equal to, and the e to the minus x over 2 is still 1. Nice. And what do you get on the next one? Okay. 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 All right. Is 2c2? Is that right? I'm lost where y'all are. Okay, good. Minus. Now C1 is a minus 1, right? So let's just go and put minus 1, right? plus 0, and that's 1 over 2, right? So I think, and that's equal to 2. So I think what we've got is 2C2 plus 1/2 is equal to 2, if I'm understanding it right. Let's just multiply everything by 2, and you get 4C1 plus 1 is equal to 4. So 4C1 is equal to 3, and C2, I'm sorry, these are C2s. C2 is equal to 3/4. Yay or nay? Okay. So now we get to plug in our solution. Y, the general solution is e to the minus x over 2 times C1 is a minus 1. I'm going to write the positive one first just because I like to. 3/4 sine of 2x, if it'll ever write, minus cosine of 2x. That's probably not how the book writes it, but that's how I like to. And that is an x there that kind of looks like a y, but it's not. Okay. So let's see how the book did. Y is equal to e to the minus x over 2. Got that part right. Now they lead off with the minus cosine 2x plus 3/4 sine 2x. That's fine. And they say, we see that it starts out as a oscillatory, is what they say. This is just some sinusoidal curve, but this has decreasing over time. Remember, we call those damped harmonic functions, and be sure you put an ED on them, PED on them. Okay, never mind. But that's sort of how it looks. Blows up for negatives. They get unbelievably large, but on positive, it's ultimately going to 0. That maybe takes over after a while. But somewhere in between here. All right, good deal. Excuse me. Now, they then throw in at the bottom of page 137 something that is pretty good, and they entitle it 2 Equations Worth Knowing. Okay, so like 2 people worth knowing, you might be able to know. Okay. Here are the first one. Y double prime plus k squared y is equal to 0. And the other one is y double prime minus k squared y is equal to 0. Okay. This first one, with the assumption that y is equal to e to the mx, what would you get? M squared. M squared. Plus, say again? Plus t squared. Say again? Not m. That's not a y prime. That's just a y. If you had a y prime term, that would have an m in it. The y term doesn't. So that's equal to 0. And do we know what the solution for that is? Not quite. Not quite. I'll even put in the plus or minus for you. Okay. M squared equal minus k squared. Does that help?
Plus or minus k squared?
Okay.
Plus minus k.
Okay. Except we're taking the square root of both sides. K, okay. Or Ki. Okay. I did it. I knew I was going to do it at some point. Okay. Ki. Let me clean that up some. Well, I didn't need to write about the plus or minus. Plus or minus Ki. There. Put a dot over it. Okay. How about on the other side? M squared. K squared. 0. What does that give you? Huh? Why do you need an I? Plus or minus K. Because now just factor that. M plus K times M minus K. Right?
Would M be plus or minus?
Say again?
Would M be plus or minus?
Yeah, M is equal to plus or minus K. Because M plus K is equal to 0, or M minus K is equal to 0. Plus K or minus K. Okay. Now, what does this one give you? With the I's in there. And notice there is no alpha. So don't call alpha. Okay. See what? Say again? See, your alpha is 0. So e to the alpha x is out of there.
Cosine kx.
Yeah, that's it. Cosine kx plus. Right?
Well, if it's the same variable, don't do the x.
I'm sorry. Yeah, but they're different functions. Sine and cosine are different functions. And they're independent. They're orthogonal functions, in fact.
Okay, yeah, okay.
Okay? Yeah. All right, how about the other side? I'll start it off for you. What was your original assumption? Yes. That's it. C1 e to the kx plus. Nope. No, because one's plus and one's minus. They're not the same. Minus kx. All right. So, whenever you have one of those forms, just know it gets to be this. Now, this is a perfectly sinusoidal function of some nature, depending on what k is and stuff, but they're the same frequencies that, I think you have big hump, little hump, big hump, some sort of pattern like that. Okay? That one, on the other hand, you have one function that's taken off this way and another function taken down this way. Depending on your C's, of course. The key C's will alter things a bit. And but those are how those functions look. Okay? So the first one is y is equal to C1 cosine kx plus C2 sine kx. The next one is y is equal to C1 e to the kx plus C2 e to the minus kx. Now, here's the part that gets me crazy. Notice if we choose C1 and C2 equal 1/2, why would you do that? But then in particular solutions you would get the cosh hyperbolic cosine of kx, and if you did C1 1/2 and C2 negative 1/2, you get the hyperbolic sine of kx. Why would you want to do that? I don't know. They seem to like those, okay? Since hyperbolic cosine and hyperbolic sines are linearly independent on any interval, alternate form would then be that this one, the second one, you could then say y is equal to, and this is not the same C1 and C2, but it's still there, just constant, C1 hyperbolic cosine of kx and plus C2 hyperbolic sine of kx. Now, why would you ever want to do that? I don't know. The thing is, it makes it look like this one more, but those are completely different functions. I mean, they have nothing to do with sine and cosine. They're just called hyperbolic sines and cosine. I mean, they may have a little something, maybe the even or oddness, and those kind of things are similar, but that's all. So, to me, those others are just, this is far easier to work with than that. I don't know, maybe it's just me, but that is an alternate form for expressing it. And they said your problems 41 and 42 in your exercise set will follow up on that, which I'm sure you want to get to as soon as possible. Okay. Now, what if you have higher order equations, higher than quadratics? Of course, what's one thing that will come to mind? It's going to be a lot harder factoring, isn't it? Okay, but here's what you would have. What if, in general, to solve an nth order differential equation, and they are making these linear, where all your a's are real constants, no variables, we must solve an nth degree polynomial equation. So I'm not writing down the differential equation, but then you have a sub n, m to the n, plus a sub n minus 1, m raised to the n minus 1, plus a sub m minus 2, n minus 2, m raised to the n minus 2, plus dot, 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 continue that on down until you get down to a sub 3, m cubed, plus a sub 2, m squared, plus a sub 1, goodness gracious, I can't write, m plus a sub 0, and set that equal to 0. Okay? Now, as you may imagine, that could turn into a nightmare. Okay? But, if you remember the goodness gracious, what is it? Fundamental theorem of algebra, is that it? I believe that's it. That this has exactly n roots. Okay? Exactly n roots. Especially if those a's are integers, or at least constants. Real constants. Okay? Real constants. They don't have to be integers, real constants. Okay? Then, these have exactly n roots. Now, what do those n roots include? Multiple roots. Multiplicity. So if you have something raised to the kth power of those n, then that's k of those. And then you have to put in your x's in front of those. Remember, like we did that before. Okay? You may also have some of these, and as long as those are real coefficients, if you have any complex roots, sorry. Of course, all real numbers are complex numbers, but I mean complex numbers with i's in them, they always show up in conjugate pairs. So then you'll have an even number of those. And those conjugate pairs, you know how to handle those. Your e to the alpha beta, e to the alpha x plus times c1 cos the other, whatever c you're using there. But everything will be accounted for by either a real root, a real repeated root, or a complex root, which always shows up in conjugate pairs. And we know how to handle each one of those, kind of, don't we? Real roots would be of this form. Y is equal to C1 e to the, what do they use? M1, they use them. If your roots here are M1, M2, M3, M4, dot, 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 up to M, n minus 3, M, n minus 2, M, n minus 1, and M sub n. Those are your roots. Some of them could be repeated, some of them could be complex, whatever. Then you have y is equal to c1 e to the m1 x plus c2 e to the m2 x plus c3 m to the m, oh, c, yeah, e to the m3x. I can't, goodness gracious. You would think repetitive things would be easier. I get them, they get worse with me. Plus dot, 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 and you just keep going till you get to the end. Now, that's if they're all real, distinct roots. You got them not. However, if any of them are multiple, then some of your solutions will be e to the m1x. How many multiplicities of m1 do you want? Name a number. Second? 3? Is that what you said? So the one would be this, another one would be what? X e to the m1x, and the next one would be x squared e to the m1x. So if it's multiplicity of 3, there they are. Multiplicity of 7, you go up to x sixth, okay? X to the 6th e to the m1x, okay? Depending on how many multiplicities you have. Now, so in that case, your solution, if that's all you had, would be c1 e to the m1x plus c2x e to the m1x plus c3 x squared e to the m1x. And then if you had others, just keep putting those out there. Whether they were real numbers with one multiplicity, in other words, no multiplicity, just the one value, or complex, and deal with those. Okay. When the coefficients are real, complex roots of auxiliary equations always appear in conjugate pairs. So for every, what did it say? Thus, for a cubic polynomial equation can have at most 2 complex roots. A 7th order could have up to 6 complex roots, but one's got to be real. Okay. So, that looks daunting, doesn't it? Until we do some, and you see they're not too bad. What about this one? Y triple prime, okay, plus 3y double prime minus 4y is equal to 0. What's going to be your assumption? Y is equal to mx. Got it. And then what would be your next step? M cubed. Okay. Oh my goodness. What do we do with that? Oh!
I'm on the right track now.
Huh?
I'm on the right track. I think I can get that one.
Okay. What would you do?
Well, factor.
Okay. It's going to be a little hard since we're missing an M term. See, that's not 2, 1, 0. That's 3, 2, No 1 in it. Okay. No. This is a
We
4.
need to add an M someplace.
Yeah, but there ain't none. Okay.
Well, just add one and then.
Here's flashback to pre-calculus algebra. It probably was a long time ago. Okay, some longer than others, but flashback. You remember something called the rational zeros test. Okay. This is a quadratic with integral coefficients. Now, this only works if you have integral coefficients. This does. So what you do, all your solutions for rational solutions, okay, rational solutions are going to be of the form P over Q. That's a ratio, right? Where P is some multiple or factor of your constant term, which is minus 4, and Q is some multiple of your leading coefficient, which is 1. So that's going to be plus or minus 1 will go into 4, plus or minus 2 will go into 4, and plus or minus 4 will go into 4. But the leading coefficient is 1, so it's just plus or minus 1. That's the only thing we go into. So you don't even need that denominator. These are your 6 possible rational zeros for that equation. Okay? Now, the easiest one to deal with is 1. And if you plug in plus 1 here, this is the one that you do this. Just plug it in. You get 1 plus 3 minus 4, and sure enough, that's equal to 0. We found one. M is equal to 1. That gives you 1 up, but you remember you got 3. This is the third order. Okay? But how do you find the next one? Good old synthetic division. Uh-oh, remember that one? Nope. Okay, synthetic division says take that root, 1, put it on the outside. Put your coefficients on the inside. What are they? 0 minus 4. You have to account for the missing term. So you have to put a 0. Always you'll have one more number here than you have maximum exponent there. Okay? And then my little rule, I've never seen it in a book, skip a line, draw a line. Okay? That's my little rule. Bring down the 4. Bring down the 1. Goodness gracious, where's my brain today? Okay, bring down the 1. And then at this point, you multiply, add, multiply, add, multiply, add. What's that? That'll be 1. 4. 4. 4. 4 again. 0. Ding, ding. We knew that was going to be a 0 because 1 was a root. This is your remainder. What does that stand for? You reduce from a cubic to a quadratic. M squared plus 4m plus 4. Once you get the 3 down there in your quotient, stop. And where do you go from here? You know. Huh? What can you do with that? Bill wanted to earlier. Huh? M plus 2 times m plus 2. So now we have a double root of m is equal to negative 2. All right? M is equal to negative 2. And m is equal to negative 2. Now, you don't need to write it that way, but those are 3 roots. I never saw it but a few times, but when I did, I almost always saw this as a dumb, I'm sorry, maybe you liked it, Bob Newhart show many years ago. He was an inn out in the country somewhere, and this guy always would come up. He said, I'm something, and this is, I can't remember his name. This is my brother Daryl, my other brother Daryl. So same thing here. Here's an M equal 1, and then his brother M equal minus 2, and another M equal minus 2. So you got 2 of them. So what can you do with this as far as coming up with your solutions? Y is equal to? Right.
C1.
C1.
And then got X up there, each of X is left, but the X bar would be.
E to the X. Is that what you said?
Yeah.
Yeah. Okay.
Next we check the same pattern, C2.
Right.
E, and then do the loop up there, minus 2X.
Right. Let's say it again. Same thing you told me. Huh?
X.
Just
Because
2X.
you got
All that same
it's like
thing,
case two
minus 2X.
X.
X e to the 2X. There it goes. Okay. All right. Remember, with repeated roots, you put in an X. And as many powers of X as you need. There's your solution. Third order, 3 independent variables. If this were a initial value problem, how many initial conditions would you need? Initial. You would need 3. One would be y at some value. Doesn't matter what value. Yeah. Y prime at that same value, and then y double prime at the same value. Never the y triple prime, but up to that. That gives you what you need. This was not an IVP, initial value problem. So, let's see what they got. Y is equal to C1 e to the x plus C2 e to the minus 2x plus C3x e to the minus 2x in the right order and everything. Good for them. Okay. Okay, we got about 15 more minutes. Is that right? Huh?
Like 10 or 11.
Okay. All right, boy, he's keeping up with it. Okay. All right, you can't wait, huh? Okay. All right. Let's go on to example 4. Oh, me. Fourth order? And they write it differently even. Look at what they've done here.
We don't know how to do this.
D4y dx to the fourth plus 2 d 2y, second derivative of y with respect to x squared, plus y equals 0. What's your assumption here?
Y equals E to the X.
Got it. Okay. And then what do we do with that?
It's M to the fourth
Yep.
plus 2 M squared
Got it.
plus 1 equals 0.
Okay. What would you do with that?
Let's go.
Yep.
Screw up all day, so let's factor.
Yes, let's factor. And what do we factor that as?
M squared and the first component, both of them.
Square. Got it. And what does that give you? I don't think so. Okay, m squared is equal to negative 1. So what would m have to be?
1.
I, yes, okay. Plus or minus I. And each of those is a double root. Because you got 2 of them.
Yep. So,
Right? Okay. I am saying that right, yeah. Okay. So each of those is a double root. So guess what? No real solutions for m. No, there are both repeated solutions but the repeated solutions are imaginary. And there's no real part to the imaginary either. So what might be your solution?
we got Y equals C1 E.
No e. What happens when Yes, that would be cosine. You don't put the I in if you're using the cosine. X, okay, plus C2 sine X plus, gotta have a C3.
Well, I guess since there's two, you can do X.
Yes, X cosine X,
And then C4.
C4, X sine X. There you have it. Because they're repeated, squared here, you gotta have two of them, so it means you got. The order really doesn't matter so much, but what they get here, sometimes they put the answer in blue and sometimes they don't, but this is y1 is equal to c1 cosine x plus c2 sine x plus c3 x cosine x plus c4 x sine x. Done. That illustrates a special case when the auxiliary equation has repeated complex roots. Okay? All right. And the thing they do note here is the betas, the part that goes with the complex, the real number that goes with the I, it says they're always greater than 0. So, all right. Then the conjugate is also a multiple of k, and so you just keep on going. They kind of lost me here now. Oh, I see. Well, no, I don't see. Oh, I see. They're going back to when they did case 3 before, and they went back to that original thing of E alpha plus I beta and that kind of stuff. That's what they're going back to at the top of page 139. But what it ultimately gets to is what we did. Now, we didn't have an alpha, but it would be e to the alpha x if you had one. Our alpha was 0, so that was just 1. Cosine beta x, and then you'd have x e to alpha x if you had one multiplicity of 2, x squared if you had multiplicity of 3, all the way up to, if you had multiplicity of k, up to x to the k minus 1, e to the alpha x, cosine beta x. You have the e to the alpha x in all of them. Okay. And what do they say here? In example 4, we have identified k as 2, multiplicity of 2, alpha was 0, and beta was 1. Yeah, we already dealt with that. Now, of course, the most difficult, how do we do on time? We got 5 minutes maybe? Or do we? Most difficult aspect of solving constant coefficient differential equations is finding roots of auxiliary equations of degree greater than 2. Yeah, we've seen that. Something we can try is to test the auxiliary equation for rational roots, and that's what I was doing. That m was p over q where the rational is expressed, blah, blah, blah. And I've already showed you that one. But example 5 will show it to you even more succinctly, well, a lot more of an issue than ours was before. I don't think we'll have time to do example 5. Do you? We have just a few minutes left. So let's pick up next time with example 5. Okay, I'm going to erase my arrow here and put my arrow here, example 5. Okay. Now, with that in mind, let's see how many homework exercises. Oh, look at that. We came so close. So you got plenty to work on here. Any of the odds, 1 through 13, I think I assigned most of those before, didn't I? I don't remember. I think so. Any of the odds whose answers are in the back anyway. Any of the odds 15 to 27 whose answers are in the back. I know I didn't assign all those because we didn't have higher orders then. So those are all new ones here. Let's see. And then I think you can do 29 through 35. Those are given initial value problems. Okay. We haven't done the boundaries, so stop there. Stop at 35, and we'll pick up the rest of these next time. There'll be plenty more to go. Okay. Any questions?
No.
Huh?
No.
Okay. All right. And let's see. We've still got some ways to go in this class, because then we got 4.4 is undetermined coefficients. And we're going to do the superposition approach, because 4.4 and 4.5 are basically cover the same, they plow the same ground, but they use different techniques. 4.5 is called the annihilator approach. Now, I've taught this both ways, and it seems like students understand the superposition, because we've been dealing with superposition before. Both of them work pretty easily, fairly similarly, but it just seems like students pick up on that. So we'll skip 4.5. Then we'll go to 4.6, variation of parameters, and some of that will be plowing new ground for me, because I don't think I've had this class to get this far before. So I've done some with that, but only once or twice. I don't see any of my marks on the page, so we didn't get very far. So we'll go as far as we can in Chapter 4. If we get, well, Chapter 4 is awfully long. We're probably going to skip some of the later ones. If we do have time at the end, we may go, and we don't do that. I don't think we do Chapter 5. This may be moot. We may not get out of 4. I don't think we do the modeling or the series solutions, but what we do, we'll go to 7 next if we get far enough in 4. We'll go to Laplace transform, because that was mentioned in your course description, if we can get that far. All right. Any questions? We'll worry about 4.3 for now, and then we'll move on, like I said, to 4.4. Undetermined coefficients. And then we'll do, if we can, 4.6, I believe it was, variation of parameters. Yeah. And we'll see how far we get from there. Because, this month, November, we have next Monday, bad news, good news, bad news situation. The good news is next Monday is Veterans Day, and that is a holiday, state holiday. The bad news is we'll miss class. So sorry about that. Get over it. All right. So, yeah. Okay. So we lose a class next Monday. Then we're here Wednesday. Then we have one more week of class. Then we have Thanksgiving is the entire week off. Bad news there. We have meetings Monday, Tuesday, and Wednesday, but y'all don't. And then Thursday and Friday are holidays with Thanksgiving. And then I think there's maybe 1 week of class in December before finals, something like that. And, of course, your final will be the last test. It may be Chapter 4, it may be Chapter 7, whatever we get to. We'll see. There's so much in Chapter 4, can't imagine we're going to get out of Chapter 4. But if we do, we'll have a test in that, and then 7. But I don't think we're going to do that. We'll see. All right. Any questions? All right. Miles to go before we sleep.
Okay. I have a lot of them, but the question is, can you work problems out?
And my answer will probably be, I hope so. Okay.
Bob said, yeah, I can, but can you?
Yeah. Now the question is, can you? Yes.